Let's get going. Holy smokes, there's a lot of people here. Are you here because it's a review day? Is that why everybody's arrived? I don't know. Maybe it's just because you couldn't see the video correctly online. If you're watching the videos as your main way of watching class, for whatever reason, this room is terrible for videos. So watch the afternoon one, the other class, the 4:30 p.m. one. It's got much better fidelity on the actual videos themselves. Okay, so we are here on Monday. If I fall over during class, it's only because I got off a plane at 7:30 this morning from Seattle, so I'm a little tired again. So my Navy Reserve job, I have to fly to Seattle once a month to do that. So
You're so tired.
I get to.
Make a midterm.
I should make. I already made the midterm. Haha.
You don't have to worry about
All that time on the plane, I got to make a really hard midterm.
Well, don't worry about writing it or anything.
Just kidding. It's not that hard. Trust me, it's not that hard. Okay, but here's what we're going to talk about today. So actually, I totally forgot to look up the final stats on this. Let me see. Somebody sent me a anonymous feedback on wanting more time on memory and memory management and memory leaks. So then I asked people to sign up. Looks like only 26 people responded to the little poll. That's fine, whatever. And 77% wanted a little bit more time on memory management. So we'll do a little bit of that today and just kind of talk about when and why we need to worry about memory management and kind of a little bit more detail on thinking about the problem. Because memory management is not hard, it's just knowing when to use it and when to use it appropriately. And that's the problem that caught some of you guys off guard for homework assignment 2, which we finished grading last night. I have to figure out now how to get it onto the web page and all that, but I should have that figured out. If not tonight, then tomorrow for that. Okay, questions so far on homework 3? Moretta wants to ask something important.
For the one there's one of the functions that wants you to print out the status of the student.
Yes.
Even though it's inefficient, do we just loop through every waitlist until we find that person?
Yeah, let's talk about.
A little bit based on what their major is.
Yeah, exactly. Yeah, I purposely made these things inefficient so that you have to see how you might have to do this. So I mean, this was not the way I might do it in real life, but I wanted you to see how to do that. Did you have another comment on that?
No.
Different question. Okay. And then Nathan, I'll get to you. The point was you kind of have to see how do I NQ and DQ off the queue, and then what am I going to do with the things that I'm DQing if I need to re-NQ them and so forth. It's not hard. I just wanted you to think about it. So that's why I made it a little hokey in that sense. So yes, it's definitely inefficient and not necessarily the way you would normally do that, but it was purposeful. So sorry if it's causing you a little headache. Sorry about that. Yes, question in the back, and then.
Yeah, for the waitlist position, I'm not sure if this is answered already, but what do you do if the status given is not either major waitlist or other waitlist?
So what do you return? I put this on Piazza, I think. -1. Just return -1. I almost certainly won't test that. Like I won't test whether or not I won't ask if a student's on, like what position in the waitlist they're not on the waitlist. Although that's a legitimate test, I could do that, but -1 in that case. Okay, Nathan, you had a question.
One thing, the enroll student function.
The enroll student function.
Actually, no, the one that finds the student, the drop student, in fact, the part that finds it though.
Okay. The drop student,
Yeah.
part that finds it. Okay, yes.
It would be more efficient to check if the condition was true after you've searched each particular thing, so it doesn't have to search something once it's already found it. But if you do that, then it doesn't call update enrollments at the end. So is it okay to put update enrollments on those checks, or should I have it do all those extraneous checks?
Well, I'm not sure there's that many extraneous checks if you do it, because keep in mind, you're going to have to DQ the whole queue and then re-NQ the whole queue. Like there's no other way around it, the way I've built it.
But if it finds it on the class roster,
Oh, if it finds it on the class roster. Yeah, you can amend that function as necessary.
then there's no reason for it to go through the other two wait lists.
Oh, sure.
It's already found it.
Well, no, that's true. That's true. It's not possible for somebody to be on a wait list and in the class. Impossible. Impossible. Should be.
Okay.
It should be no way to have a person go onto the wait list. Well, there might be a way, but I won't try to enroll the same person twice if they're already enrolled. I won't do that. Susanna.
If you wanted to drop everyone, like every waitlist in all the classes,
Sure. If you want to drop everyone.
Yeah, so like everything is empty.
Yep.
Should it still like run and like go through the whole code, or should it like exit at something?
I'm not sure what you mean.
Because like I have like a check of like if the queue is like whatever list I'm in is empty, then I exit automatically from the code because that would be like a bad thing.
Oh, I see. No, you shouldn't exit on a bad. I mean, the queue can be empty.
Mm-hmm.
They can always be. They could be empty. There's nothing against that. So no, you shouldn't exit the code. Does that answer it? Okay. Yep, Rana?
When you said there was no way to do it except by dequeuing everything and nqueuing,
Yes.
if we think we have a way that doesn't do that, does that mean our way is wrong?
No, I just don't know that it's possible.
Like,
I'm not sure how it's
The
possible.
way I did it was I would dequeue and then I would nqueue it back.
Yep.
then
Oh, and you'd keep a pointer or something.
Yeah, to go around. So
Uh,
But then
I
you
mean,
have
I'm
to
still
know when you're at
dequeuing
the beginning
everything.
again.
You have to know when you're at the beginning again, because you have to have the first person. You have to have it right in the correct order.
I put like a fake student with a fake name.
Okay.
And then certain
All right, that's
like-
fine. If you can come up with ways, and that's perfectly fine. Yep. I won't enforce doing it the other way. If you want to do it that way, that's cool. Other questions on homework 3? Due Friday. Going all right for most people so far? If you haven't gotten a chance to look at it yet, you're late. Like, you will be in trouble. I can tell you that right now. So start it tonight if you haven't. If you have specific questions, see me after class or in office hours. Okay? There have been some TA office hour issues, TAs maybe not being where they needed to be. If that happens, please email me so I can put the hammer down. Right? They're normally really good about it, but sometimes things get slipped, so we'll do that. Okay, other questions? We're going to talk today about midterm review a little bit and a quick Unix tip of the day. Yes, question, Ben.
Remember, where you said you had a copy of last year's.
Last year's midterm, check Piazza. Yep, and actually I believe I put it on today's lecture slides on the web page as well. You can look at last semester's midterm. It will be similar in difficulty. All the questions will be different. Okay. Anything else before we go? Okay. So here's what we're going to do today. Unix tip of the day quickly. Memory leaks. We'll talk about that. I'll answer all your questions about that. And then we'll go into the midterm and how to prepare for the midterm, when it's going to be, what it's going to be on, et cetera, et cetera. Okay? All right. So who's run into this problem where they've run out of disk space and they've had to delete like core files and things? Have you guys looked in your like Comp 11 folders and seen that those were some problems? Like oops, I didn't know to delete all those. So one thing I wanted to talk about, you can use the zip command to compress all your files. So let's say you're not planning on going back and like reviewing all your Comp 11 stuff for a while or ever, right? You can zip it and compress it into a folder and then put that folder, like SCP the folder or copy the folder to your own computer and delete that whole folder if you want to. Or delete the whole zip file too. Here's how you would do it. There's a command called zip. There's also a command called unzip, which does the reverse. Okay? And here's how you might zip your Comp 11 folder, for instance. Let's say it was in the desktop/Comp 11 folder, right? What you would do is you'd change to the desktop directory, and then you type zip-r, which stands for, what do you think? Recursive, actually, because it recursively goes through all your folders and gets all the files in there. comp11.zip is the file that things are going to go into. comp11/* is all files. And then there's this interesting one, -x *core* says ignore anything that has core in it. Kind of nice. Even if you have all those core things, they don't get put in your zip file, so it keeps the size small. And then I said rm-r comp11/, and that will delete the original file. You might want to just check to make sure that you did this right before you do the rm-r, but that removes the whole Comp 11 folder recursively. Okay, so that's what you would do if you wanted to zip up your files. To unzip the comp11.zip file, just say unzip comp11.zip. Whoop, it unzips it all. Yeah?
If I wanted to go through and delete all of the core files within the comp11 folder,
Yes.
is there a way to use -r to make
There's a way, yeah, you can, so about 4 or 5 slides, or 4 or 5 lectures ago, I put up there how you would delete that using the find command. Yeah, which does that recursively as well. Yeah, so otherwise, there's no other real way with remove to do that. Yeah, you can't do it with the rm command directly. You can do that. Okay, any questions on that one? Quick little Unix tip of the day. I don't have an Eclipse tip of the day. Are people still having some issues with Eclipse? I know a couple people are. Susanna, what are the issues? What's hard to figure out? The debugging. Yeah, well, the debugging, look, the debugger is really powerful and does take a little while to figure out. Yeah, yeah. Maybe I should have a debugging session sometime. But I mean, I've done a couple in class, but it is tricky. Ben?
Basically, it seems like my corrections are different depending on what computer I'm on.
Your corrections are, that's probably weird. Maybe you're using GCC on one and Clang on another or something. I don't know. But your changes shouldn't be different.
Yeah.
The changes shouldn't be different, yeah. Somebody over here had a, yes?
I didn't download it locally, but for some reason GDB is not working.
Yeah, are you on a Mac? Who was I just talking to about this? Yeah. What was our decision to do? Re-download GDB. If you can find GDB, I've got a solution. If you can type GDB and it will run, I've got a solution. But if you may not have installed it correctly. But that's not a hard fix. I can see after class about that if you want. OK. Yes?
Normally
John.
when I run my program in Eclipse, I have different outputs from when I run from the
When you run the output from Eclipse, you have a different than when you run it on the command line. That's weird. Like that shouldn't be happening. So either it's not compiling in one, it's not compiling again in one or the other, or you're not in the right directory. That might be the other issue. So, but I'm not. It should be exactly the same. The output should always be the same, unless there's some. Now there could be like a memory issue or a bug somewhere that's causing different outputs. That could be the other issue. If you are getting different issues, it's probably a bug, or something's wrong in your compiling thing. So.
when I run print, when I maybe do a C error something,
Yeah.
it prints that C error and then prints everything else.
Oh, C error may not work in Eclipse as the same. That may not work the same. Yeah, I don't know. Between you and me, I would avoid using C error. I wouldn't use it at all. I would always use C out instead of C error, to tell you the truth. I know you probably learned that different in Comp 11, but I wouldn't use it at all in general, because I try to use the debugger, because that's but it's occasionally use C outs to make it do it. But yeah, the C error is probably where you're going to find some differences. It should still print all the messages, but maybe not in the right order. Yeah, that's about it. OK, sorry about all the Eclipse issues. So do a show of hands. How many people are happy that I've kind of suggested you guys use Eclipse? About a third. How many people are like forget it, I don't even use it anymore? More. OK. All right. Interesting. I'm happy for you guys to not use it, but keep in mind debugging is a lot easier when you have an actual debugger. Learn GDB or learn to use Eclipse in the debugger there. Yeah.
I feel like, I don't know if other people are running into this problem, but for me, like I use a VM for a Linux machine
Yeah.
when I'm operating at home, which is a little bit slower to begin with.
Sure.
And when I run Eclipse, it's super slow.
Through the VM? Yeah. You could probably install Eclipse locally if you wanted to. It's kind of a pain. Did that with some other people, but you can do it that way too. It is slow. The way we've got it going, it's kind of slow. It was a trade-off I had to make to do it that way. So, all right. Well, maybe next semester I won't do it. We'll see. Maybe at the end of the semester I'll take another poll and you guys can tell me it was a dumb idea or a good idea. OK. It's what? It has its uses, I think. But all right. OK. Let's talk for a few minutes about memory leaks, because some people wanted to talk a little bit more about how do you actually find memory leaks. Now, two questions. Yeah, what are memory leaks, really, right? So that should probably be the first question. The questions I have up here are why do memory leaks occur, and what do we have to do to make sure they don't happen? So I guess the first question really is, what constitutes a memory leak? Anybody want to give a gander at like what constitutes a memory leak? Yeah, Ben.
When useless data is not erased?
When useless data is not erased, that can be a memory leak, yes. And in many cases it is. It's a little more subtle than that, but that's very good. So, Senna? When you allocate something on the heap and then you don't delete it. Now, yes, that's a good definition of a memory leak. It depends on when you do the deleting. So the bottom line is, at the end of your program, all of your memory that you asked for does get deleted by the operating system. Like in the end, if you have all these memory leaks, it still gets deleted by the operating system. So that's the good news. You don't end your program and still have these memory leaks. But while your program's running, you could use more memory than you should be because you don't do the deletions when you need to. Okay, good. Who else had a comment they wanted to? Anybody else? Okay, yeah, go ahead. The core dumps, yeah, the core dumps are generally from when your program crashes. Like that's what causes those. So if your program actually crashes while it's running, sometimes it just freaks out and says, I don't know what's going to happen, you figure it out, here's a core. And what that means is it like takes all the memory that you've had and just dumps it to a file. And it's hard to read and whatever, but some people debug using those. So that's it. But those can be caused by memory leaks. Well, those probably aren't caused by memory leaks so much as just a regular bug. But yeah. Okay. So we've got this idea of useless data that we want to, but we don't remove, and just using the new keyword and not not using the delete keyword on whatever you did for new. Those are the two kind of key principles here. Okay? That's why they occur. Like you don't use new and you don't use delete. What do we have to do to ensure they don't happen? We have to keep track. Like we have to figure out let me give an example. Let's say you have a function, okay, and it's I don't know, it's insert into a linked list, right? Insert, right, and you have something there, and this part doesn't really matter, but in here you say node star n equals new, right, node, like that. Okay, and then this goes into your linked list somewhere. Okay, does that make sense? So let's say you do this 3 times. How many times does delete need to get called? 3 times. Okay, so let's say you have 3 actual nodes that you've created here. Okay, the head and whatever. And there's 3 nodes here. At some point during your program needs to delete all 3 of those. Many times that happens in the destructor. So if you were to do insert 3 times, and that was all you were going to do for your program, the destructor would then say, when the program's ending and the class is no longer being used anymore, the destructor says, go through the linked list and delete everything that's in the linked list. Would that do it 3 times for this linked list, if you wrote it properly, right? Okay, so in that case, if you were just doing inserts, you need to call as many deletes as you did inserts. Now, let's say you also did a delete function, right? Delete node star n, right? And in this delete function, it comes to your linked list and it says this one's gone. And how do we get rid of this one? We make the next pointer of the previous one point to the next of the one we're deleting and so forth. When this one's gone, doesn't delete need to get called? Okay, so delete, you call it within that function, right? Well, sorry, yeah, you call the delete within the delete function here. I probably shouldn't use delete. I probably should use remove because we've already got a delete function. But when you call the remove function, inside that you have to, if you're removing that node, inside there you have to delete the node at some point, right? Okay, and that's when it gets called in that case. Okay. All right. Let's play a little game here. I do 5 insertions, right? And I do 2 removes. 5 insertions, 2 removes. Okay. How many total times does delete need to get called? 5 total times. Where do 3 of them get called? In the destructor. Where do the other 2 get called? In the remove. Now, have we accounted for all of that? Okay, so that's how memory management works in general. As long as you figure out what's going on in your data structure, and you know that if you ever don't have a pointer to something, it's going to be lost, then that means you haven't deleted it properly, right? So, or you have to delete it at that point. Okay, so that's kind of like the bottom line in there. Now, other people are getting errors like double freeze and that sort of thing. Double freeze are a different issue altogether. Okay? I hesitate to go over copy constructors and operator overloading and all kind of advanced things. I hesitate to go over those. I've written, in the first couple of assignments, I wrote copy constructors for you. But what's happening is sometimes you might be saying something like this. Node n equals head, or something like that. Now, that wouldn't actually even work. Node n equals star head might work, if this is a pointer, right? What this is saying is, create a node for me that's local to the function, and then copy the head details into that node. If you don't write a copy constructor properly, this gets basically, it doesn't copy everything. Well, it does. It copies all the details plus just the pointer, meaning that this node and the head still point to the same like internal pointer, when many times what you really mean is I want an actual copy of this. Okay? It's kind of an advanced thing. I don't want to go into more details about it, but when you find yourself doing something like this, it will many times break because you've now gone and tried to copy something that's an object and you haven't written this copy constructor for it. Again, it's advanced and I don't want to go into too much details, but this is what's probably causing a lot of those double frees if you're doing stuff like that. Okay, what you really want to do is this. You want to say node star n equals head, and that does this create a new node? No, it just creates a pointer, just creates this nice little pointer n which says where's my node I'm going to point to, right? And that's what this creates. If you don't have the star, it creates a node for you and says I want to populate that node. Most of the time that's not what we want to do. Okay, most of the time it's not. And I don't think there's too many cases in the rest of the class where you'll have to write copy constructors, like there shouldn't be. But if there are, I'll try to either walk you through it or write them for you or whatever. Okay, it's kind of advanced. If you go on to programming C++ in the real world, you'll probably have to learn those things. But it's a little more than I want to talk about in like this class. OK. Other questions on memory management? Yes? Good question. The destructor gets called when you either exit the, like, how should I put this? When you have a function like main, right? And in main, you do something like q, like that. OK, that says we're creating a queue that's going to be good for the whole main function. So when main finishes, the compiler knows to tell the program that, hey, everything that it created like this needs to get deleted, and that's when the destructor gets called. So it's generally at the end of your thing here. Now, if you had another function, right? If you had a function like, I don't know, the remove function or something, right? And in there, you did the same thing. At the end of this function, that destructor gets called. So it gets called whenever the compiler says that function is not used anymore, or that object is done. And it can figure that out.
What if it's like very simple not instructions like ints or strings? Does the destructor get called for them?
So ints don't have the fundamental data types. Ints, chars, floats, doubles. Those don't have destructors. They're not even objects really. In other languages they might be, but not in C++. Strings are objects, and they do have their own destructor, but you never use them because it's already built for you. But most of the other things you build, you'll have to put a destructor in there yourself, like the queue and so forth. Okay, all right. And a lot of times within queue, like the queue is what? It's a dynamic array, and so you just delete the whole dynamic array using delete bracket bracket. Whatever you're calling it, queue, array, or whatever, at the end in your destructor. That's about it. We had one over here and then a couple over here. Yeah?
Are we going to have to know the operator overload for the exam?
You'll not have to know operator overload. On last year's exam, I did do that, but not this time. Nope. Nope, did not cover it. Yes, Meg?
Okay, so when do we have to, like for the node n equals new node versus just like the node n?
Yep.
I'm confused about when we need to like use the new.
You will very infrequently do this.
But like for homework 3,
Yep.
and I know there's a question on Piazza about like the queue.
Yeah, so, right. So think about what that one's doing. That temp queue or whatever it is. So what you do is I put this in there for you, I believe. Something like queue temp queue.
Yeah.
right? Now, and somebody said, why is this not a new? Why don't you use new for this? Well, the temporary queue in this case is only being used during that function, and then it's going away. So I decided that if it's only being used during that function, I could do new blah, 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 and then at the end of the function say delete temp queue, or I could let the compiler handle it for me. Doing it this way creates the object, and then the compiler says, oh, the function's done, I'm going to delete it for you. That's the difference.
But I guess, like, what's the difference? And I didn't take C++ before this, so I don't know.
Oh, right, OK.
Whatever.
Yep.
But, like, what, I don't know, like, what's the difference in those two?
Yeah, this is.
Like, I know that you have to delete it, but, like, what else?
You don't have to delete this one.
Right.
Right. So the difference is when you do this, it gets a little crazy. But when you do this, this goes on the stack. When you say queue, temp queue, without the new business, this gets created on the stack. And when the function ends, that stack gets wiped out, and it calls delete on whatever's on the stack, and then that's it. When you do queue star temp queue equals new queue, like that, when you did that, that says, hey, memory system, give me some memory. Hey, operating system, give me some memory where I can put this that's not related to the program itself, and I'll know to delete it later. That's what you're telling. It's a different place in memory. Those are the two differences. This one gets created on the stack. This one gets created on what's called the heap. And I shouldn't have the star there. And and those are there's just two different parts of memory system. This one says, I'm going to ask for memory specifically and then know to delete it. This one says, compiler, you handle all that business.
Okay, so if we're doing something in, like, just within, like, a certain function, a holder,
Yeah.
then that would generally be the case where we would not.
Yes. You wouldn't use the new.
Right, okay.
Many times you will use a pointer, like when you say node star n equals head. That's just saying, hey, I want to use that head pointer without changing the head pointer. Head's always going to point to the first one, and can point to the first one, then the second one, then the third one, then the fourth one. But you're not creating a new object for that. Whew. Ben. Oh, then yeah, Ben.
Yeah, I believe this was covered earlier. So I understand star temp queue means create something that points to a new queue.
Yes. Well,
Is that right?
node. If you've got star temp queue equals new queue, that points to a new object that you asked for from memory, and it creates it. Yes.
Yeah. So
Yep.
So what does that mean when you take out the star? It means
When you just if you took out the star and tried this, would not work. It would give you an error saying pointer type versus object type can't. It won't compile. But when you do this and just say queue temp queue, that creates an object on the stack that you can use during your function and during your function only, not throughout the rest of the program. Those are the big differences. Yeah. Moretta.
I know there was an example of this at some point, and I couldn't find it last night. When you're deleting a dynamic array, there was one time, I thought it was homework, but maybe it was a lab, that we looped through the array and then dynamically had to delete things. When would you have to do that?
If you, that's a good question. When would you have to do that? It's a little tricky. If you created the array and it was like an array of pointers, and then each one of those pointers you called new on, then you would have to loop through it. I don't even think we did that. I don't believe we did that in the lab. Maybe we did, but I don't believe it.
Or it was referenced or something. I know it,
Maybe,
I heard it
yeah.
somewhere.
Maybe. I'm not sure. By the way, the other answer to a lot of these things is to use a reference instead of a pointer, kind of like what we did in the last lab. It's another topic altogether that we probably shouldn't get into right now. But just bring it up. Yanni.
I was just going to say, I think it was the one with the pirates.
It was the Hookbook lab.
It was the Hookbook lab. OK, maybe. I'd have to go back and look at it. But it probably had to do with the fact that we had pointers to pointers, basically. Yes, Nathan.
Each object we had in the array had another dynamic array inside it.
That was it. Each object in the array had it. So it was basically a pointer of pointers, which is another kind of advanced topic. But one you'll get to in Comp 40. For those of you taking Comp 40, you'll do that a lot, actually. You'll actually do pointers to pointers to pointers, I found out, and you don't want to go there. OK, other questions on memory management? Do we have a little better idea? OK, Janet?
So when you create the new and when you just create a variable, do they work the same
They work more or less the same. When you do this, you've created a pointer, and remember you have to do an arrow. When you do this, you can do temp q period whatever. That's the big difference there. Again, this says this is a pointer, so I got to go to the object it's pointing to and then use its elements. This one says I'm using the elements directly from this q here. That's the difference. I know this C++ stuff is tricky. Unfortunately it's like sidestepping the data structures issue, which is not what I want to do, but it's probably good that you learn this. When you get to Comp 40, for those of you taking it, you'll be happy. OK, other questions on memory leaks? This is basically what we already went over. So you can read these slides, but basically it's saying if you replace an object in a data structure, you got to delete it. If you don't replace it, the destructor will do the deleting at the end. OK. Whew. We did that. OK. Let's go on to the midterm study tips and guide. OK. So for those of you who took Comp 11, I believe you were allowed a one-page back and front like kind of cheat sheet, if you will. You're welcome to do that as well. OK. I would like it to be handwritten. There are certain circumstances if you have certain accommodations, you can do it typed or whatever. But please don't type yours, because then you'll end up like bringing like a magnifying glass and having the entire book or something. And that's not cool. There's an urban legend about a class who the professor said, anything you can carry into class you can use on the test. And somebody carried a graduate student in with them and sat down. Which, I mean, letter of the law, not spirit of the law, I suppose. OK, so you're allowed to do that. In the past, I've collected those so that you don't like just give it to your friend in some other class. I'm just not going to worry too much about that, honestly. For what it's worth, this midterm, because I'm going to be gone, it's going to be given by graduate students. There's going to be 4 people in the room. 1 graduate student, sorry, TAs. 4 people in the room, 1 graduate student, or maybe 2, and 3 undergraduate students. And they will try to answer your questions, right? I will be very strict with them about collecting at the end. None of this like, give me 5 more minutes, give me 5 more minutes, right? Like when they say it's done, your pencils go down, and I'm telling them to write down anybody's name, and I'll take points off if you don't do that. That makes sense? They will give you a heads up. They'll be like, in 5 minutes, we're going to tell you to stop. And you've got 5 more minutes to finish up. OK? Here's the tips. Look, go back and review the PowerPoint slides. Review your notes, obviously. Any of the code samples I gave you, not a bad idea to go review the labs. Just read through the code for the labs. Videos, if you want. As I said, the other videos are better for the screen. You'll be able to see those better. Read over homework 1, homework 2. I will have the homework 2 grades back by today or tomorrow morning, so you'll have some time to do that. And that's that. Ben.
Where do you access the PowerPoint slides?
The web page. Just go to Google, type Comp 15. First site that comes up is our home page.
Oh, yeah.
On there, lectures are one of the tabs, and they're all listed there. OK? Miranda.
Since there's so many different like structures and stuff this is covering, are we allowed scrap paper to draw out things?
You're allowed scrap paper. I'll try to remind the TAs to bring scrap paper, sure. I mean, if you want to bring scrap paper, you can bring it, but just nothing else that has writing on it besides the one page.
15 notes. We knew they were there.
I know, exactly. All right. Questions on this, what you're allowed to bring in? If you want to bring a calculator, I don't care. It's not going to help you much on this one. Don't bring a calculator that's like programmable, like you can type stuff in and all that, because then you could type stuff in, so don't do that. No web-based calculator, like you can't use your phone. I'm using it as a calculator, no. OK? All right, other question on that, logistics-wise? OK. All right, here's the types of problems I'll be asking. This is very similar to if you looked at the one from last semester, it's very similar. There will be some short answer type questions, like explain where a linked list is better than a dynamic array, right? Not sure there is. Well, there are. Yeah, there could be if you're like deleting at the front or something, right? Easy to do. If you only need the first element, yeah, exactly.
Q's better use linked lists instead of dynamic arrays.
Are which? Q's? Not necessarily. Sometimes they are. Yeah, in some sense they're better. If you keep a tail and a head, sure. And that's sometimes better. Yeah, maybe not in the end necessarily faster, but about the same. About the same, yeah. Okay, you'll have to find some bugs in code. That tends to be really hard for some people, right? I mean, you read through and you go, now the bugs will come in like 3 different flavors, right? I'm not gonna worry about syntax errors. Like I'm not gonna leave off a semicolon and go, aha, you missed the semicolon, right? Right? I'm going to make it so that there's something significant that's wrong. Now, it may not compile. Like I'm not necessarily going to give you something that absolutely compiles. It might, I mean, which is kind of silly because if you really have a non-compiling one, it would find it. But in some cases, like I want you to be able to read through and go, oh yeah, that's definitely something that should not be there. There will be bugs of too much stuff. Like let's say you did something like where you created a node and you weren't supposed to create the node and you tried to copy it. That might be a type of bug. Bugs of omission, which are the hardest to fix. Like you should be doing something in this function and you're not, right? That's a hard one to catch, but I'm going to put 1 or 2 of those. Yeah, Al?
If we fix the bug and there's like a minor syntax error.
No syntax errors will not count. I mean, unless it's just really like wacky, I mean, if you put, if you forget the semicolon, I'm not going to take points off. That's yeah. But please try to do good C++ code. But that's not like minor syntax errors. I'm not concerned about. Yeah. Charles?
So what degree of these bugs are they going to be in the sense that like this code would still compile?
Most of the time it will still compile, but there'll be something wrong with it. So a good one is like an off by 1 error, right? You're supposed to look through the whole linked list and you forget to go all the way down to the first element or all the way up to the last element or something like that. That you do have to read the code and go, what's happening here, and what am I doing? What am I doing wrong on that? That's the things like that. I mean, I want them to be things you have to think about in that case. Yeah.
So would like a non-compile error be something along the lines of you go through a linked list and you try and take the next tail, but it's actually null?
No, that would not be. That would actually compile. Yeah, sure, because the compiler has no idea what your nodes are and it doesn't care. That would segfault. Yeah, segfaults are. Yeah, if it's going to segfault, that would be a good bug to make you debug. Yeah, take out. Okay. Yes.
Would you tell us how many bugs there are?
Yes, I will. I will not say there are some bugs here. Find them. I'll say there's 2, 3, 4, 5, whatever. I will tell you how many. I don't necessarily think that I always need to do that, but yeah. I'm not going to make you like search for hours. Ooh, yeah, that would be mean. Find the differences in these 2 pictures. Oh, I hate those, right? Yeah. Okay. Other questions on bug finding? Okay, you will have to write some code. Okay, so I wrote the mid-year exam and I showed it to a couple people and I got one comment that said, there's a little too much code to write in here. And then I got another comment that said, not enough code. So I'm going to leave it because it sounds about right in real, for real. But the code that you have to write will be short pieces of code that you've probably written before for a homework assignment or a lab, like not the same exact one, but very similar ideas, right? Ben?
Will we be allowed to bring in blank sheets of paper?
Yeah, you can bring in some blank sheets. Yeah, you can bring in some blank sheets of paper, or I'll have the TAs have blank sheets. It's probably the easier thing. Yeah. Okay. By the way, in here, it is really crowded. Okay. I'm also going to expect that you are looking at your paper. I mean, I hate to have to say that, but the TAs are going to be looking for that, and I'm just going to say, if you see somebody blatantly looking at their neighbor's paper, take them, and then we'll talk later, and you can try to convince me why you didn't cheat. But you can bring paper in. Okay. Other questions on short code writing? Not going to be too hard, but legitimate. Yeah.
When you said like the possibility data structure you haven't seen yet, does
Yeah.
that mean like be writing one or be using?
Well, I could say, hey, this is remember I mentioned this the other day, a double-ended queue. I don't even think I knew what it was called. A D-E-Q-U-E-U-E, D-E-Q-U-E-U-E, right. A deck is like a double-ended queue where you can actually remove from the front and the end. Now, we haven't explicitly talked about that, but that sort of thing is fair game if I tell you enough about it. Like I've got to say, hey, a deck is an abstract data type that allows you to remove from the front of the queue or the back of the queue, but that's it. And then I would say, write me the function that removes at the back of the queue or something. So something like that. I've seen in the past where professors have said, here's a brand new data structure on like a completely different topic, and I'm not going to do that to you. I'm not going to do that to you. Yeah?
How do you spell DQ?
Is it, I think it's actually that, DEQUE, I think is a deck, is what I think it is. Yeah, you're right. I think that's what it's called, the data structure. But how do you spell DQ, DEQUEUE?
I just spelled that
Yes.
wrong so many times during this code. I like the
Oh.
last QE.
Yeah.
I get mad at me.
I know, I do it wrong too. Okay. So short code writing. Explain what code does. Like I might say, hey, what is this code going to do for us? Right? What's this code going to do? And that's kind of a Comp 11 type question, I think. You probably had to do stuff like that. Maybe not. But I will ask you more about the big O bounds for your code. I'll say, hey, what's the asymptotic behavior for this code? It might be a code snippet, or it could be just a function. We'll go through some examples up here in a few minutes. Okay? Explain some C++ stuff like, hey, what is this destructor thing? You have to know what the destructor is. I will not ask you copy constructors or the ones we haven't just covered yet. Yeah.
For
Sure.
big O, will we only have to determine like the order and the behavior, or will we have to show like it's between like 5x?
No. You will not have to do anything more advanced than the. I could ask you the average. I could ask you the best case and worst case. Now, average being if in a generic data structure like a tree, we know it's log n, right? Like that's the average, right, for a tree. But I could also say what's the best case and worst case. And we've gone through some of those in class as well. Yeah, Ben.
What are big O bounds?
That's the O, N, O1, O log n. I'll show you some examples in a few minutes. Asymptotic behavior.
Oh,
Yeah. Okay. All right. So those are the types of problems. Okay, pretty standard stuff. And again, I'm really not trying to trick you on any of this stuff. I want you to prove what you know to me. Honestly, I would be perfectly happy giving everyone an A. This is not like trick people into doing badly on this. Here's what we've covered here so far, right? We've done some C++, of course, static and dynamic arrays, linked lists, recursion, right? You probably will have to write something to do with recursion. Stacks and queues, and then trees. And trees covering both like generic trees, like the ones with many leaves, or many children per node, and binary trees, which are the slightly easier to understand ones and more often used. And then, of course, asymptotic notation. I think that's about all we've covered so far. Retta, what else have we covered?
No, just a question.
Yeah, no, go ahead.
For recursion, like so far all the ones we've done, they've been pretty like, not hand-holded, but there's a lot of like, okay, you're going to make a recursive function. Like when we did the maze, and we
Yeah.
kind of, like took it through it, would we be expected to come up with recursion our own, or are we going to be given a thing and say?
So I'm actually still debating this. I've got a problem on the test right now that you have to do some recursion, and I've given you enough hints that it's not going to make it too taxing. But some people have looked it over, said, take that out, just let them do it. And so I haven't decided yet. But it's not going to be too hard. I think the hardest it would get is remember those tree ones we did on like a couple days ago? Those ones got a little bit tricky, but that would be as hard as it gets, right? Probably not as easy as doing like, finding the, B to the n. That was a little too easy. But doing some of the tree ones got a little bit trickier. Okay. All right. Go back and look at the notes on those ones if you want. All right. I don't think we covered anything else in particular that we're going to cover on the test. Anyone want to throw any things out that they thought they might have to study? Sets. We did cover that. I'm not going to cover that. I'm not going to ask you that on the test. Anything else? What's that? Cowspeak, yes. So look, I will give you a hint. If you were in class, you have the opportunity to get some bonus points by paying attention in class. So you'll see what that means on the test. But if you did not come to class or watch the videos, you won't get those points. But they will just be bonuses. Okay? Alex?
Oh no, sorry.
Okay. All right. Let's go through some of these topics. Okay, C++. So we talked about destructors. We did a little bit of that today. You should know, basically the idea of a destructor is clean up your business at the end of the program, or at the end of when your class is being destroyed. Okay, anything that you said new to, you have to delete. It's really about all a destructor needs to do. Okay? This dynamic versus automatic memory, this is the stuff we were really going over today, right? New versus just saying Q, QUEUE, Q the letter, right? Like this. Q temp Q is different. That's called automatic memory versus dynamic memory where you do the new function. Maggie.
Okay, so if you have a pointer
careful, careful, careful. At some point in your program, you did use a new for the thing that's going to point to. I'll leave it at that. But so remember, so let's think of a linked list. Okay, we think of a linked list and we say, hey, at the beginning, head points to what? Head points to null. There's no head points to null. There's no node yet, right? Head is a pointer. So far, we haven't used any news yet. But then I go insert at head a new, insert at head some value. In that function, I use new to create a node, and then I say head points to it. So now head is actually pointing to the thing that I did new on. Later, I can say I want to walk through the list. I can say node star curve or current equals head. OK, that's a pointer. I don't use new again, but now it's pointing to whatever head is pointing to. And there was something that I used new on earlier. Like that's how it works there. So there's not necessarily a one-to-one relationship between pointers and things you use new on.
Okay, so can I ask you a question about the homework?
Yeah.
Okay, so because on the homework I tried to do like the Q and then like have temp Q as a pointer.
Yeah, you can do that.
And then, but then I tried to NQ on it.
Ah.
And it was like temp Q isn't initialized yet.
Yeah. Sure, because if you do it as a pointer, then you've just said what you do when you say Q U E star temp Q. When you say that, what is that telling me? What am I creating right here? I've created a pointer to a Q. I've created something called temp Q, which says I need something to point to, but I haven't pointed it to anything yet. Right? So that's why it's saying it's not initialized. Right now it's pointing to who knows where.
Okay.
Right? If you say equals new Q, guess what? The memory system says, oh, here's where you can point it at, and I'm going to point it there for you.
Okay, and then it's able to.
And then it's able to NQ on there.
Okay,
Yep.
got it.
And in that case, you'd have to do temp Q arrow in Q
Right.
because it's a pointer. Yep. But you could do it that. But then at the end of your function, you have to delete the temp Q. Yep. So a lot of times we don't bother because we know if you're gonna do new in the same function you're gonna do delete every time, don't bother doing the new. Just make the compiler take care of it. That's the general way. Okay. Whew. Okay. Yeah, Ben.
So when deleting temp Q,
Yes.
you just delete temp Q, or
Yeah.
just delete the pointer?
No. That delete does never deletes a pointer. Delete doesn't have any. The pointers is going to stay forever. Well, stay for the whole function, right? But when you say delete temp Q, right? What that does is it calls temp Q's destructor, calls the Q destructor on temp Q, and then cleans up after itself. And then temp Q, the variable, still points to that location, which has now been deleted, so you don't want to ever use it again. But it still points there. Okay? We see that when we do the expand in a dynamic array. You delete the dynamic array that you had, the first one you had, then you reset the same pointer to the new dynamic array. And so you're not deleting a pointer in that case. Okay? Yeah, so
Temp Q is a variable in the stack, right?
Yes, temp Q itself is a variable on the stack. What temp Q points to in this case is on the heap. Yeah, that's a good point. Whew, it's a little hairy, but that's a good point. Yep, good. Yeah, Jonathan. Yeah.
So in expand, you say you create a new temporary Q or a new Q array and then put everything in it and then delete the array itself. Then,
Yes.
Point back the array to like.
Yep, in the expand.
Do you need to delete the array that you create?
No, why would you do that? Everybody tries to do that, but then they segfault. So don't do that, right? Remember, you're trying to propagate this array through the rest of your program. If you delete it, it's gone. And this is a very good point. Here's the original dynamic array. This was, say, I don't know, ARR, right? Points to the array. OK, we create a new one because we're expanding it. We use the new keyword, and it gives us one that's twice as big, right? Then we copy everything over, right? Now we've got this big one. Now where does array point still? The old one. So then you say delete array, the old one. And it deletes this. And it says that one is gone from memory. Where does array point now? Still, no, it doesn't. It still points right there. But this stuff is all gone. OK. Now you say array equals new array. Where does ARR point now? It now points to here. Where does new array point? To here. If you said delete new array, what would you delete? This thing. That's the one you want to keep. So you don't delete that one until the destructor. And in the destructor, it will delete array, which points to that one. Does that make sense? Yeah, it's a tricky concept, but it makes sense. Alex and then Chuck.
So if every time you expand the array, right, you have a new pointer that you create in that method.
Yeah.
Is there like, I know it would be like almost inconsequentially small, but would there be a tiny memory leak because every time you make a new pointer?
Why not? Because it's on the stack. And when the function ends, that pointer gets taken off the stack and it's good to go. Perfect. OK, Charlie. Same question.
When deleting array,
Yep.
you need a bracket there between delete.
Oh, yeah, you're right. Sorry, you would need a bracket. Thank you. Good call. Good call. OK, other things on that? Whew, we're getting there. Yes?
So, just in the same homework problem, when we have a wait list and then we execute it until it's empty.
Yep.
And do we somehow delete it somewhere, or so my question?
It will get deleted when main ends, because that's where it got, or it will get deleted when ISIS course ends. That's where it will get deleted. But remember, if you're looking through the wait list, this is back to homework 3. If you're looking through the wait list and you're dequeuing all the students off the wait list and in-queuing them into some temp queue, then you have to have another function to dequeue them from temp queue and re-enqueue them back into the original queue, so you don't delete it. That's probably the best way to do it. Now, Moretta here is jumping through hoops to do it a different way, but it's not a bad way.
Oh, I thought it was easier because I didn't.
Might be a little easier. You didn't need a temp queue.
I just kept DQing and queuing for like
Yeah.
a while until I got back.
Yeah, it's a good idea. It's a good idea. Until I create a fake student that has the same parameters as your fake student.
That's just me.
I'm going to look through your code and make it do that. You have to be careful with that, though.
Yeah, what's your fixed student?
What's that? What's my fake student name? I'm going to look at Moretta's code and tell you. OK, so those are dynamic versus automatic. OK, what's the difference between an ADT and a data structure? Yeah, go ahead.
So an abstract data structure, well, an ADT is defined by the functions that are in the code, whereas a data structure is like already decided in terms of like.
Yeah, a little bit more than that. An ADT, an abstract data type, is defined by the functions it can do. Right. A data structure is like the underlying part of it, right? Yeah.
Like you use pre-existing data structures, but that restrict the way you manage them.
Yeah, that's a good way to think about it. The ADTs use pre-existing data structures, or they use data structures but limit the way they can be used for reasons of good asymptotic behavior or simplicity or whatever. Yep, or safety in terms of you don't want somebody mucking around in the middle of your array. That's another reason. Good.
Not sure I follow.
Not sure you follow what? The difference?
What are examples?
Yeah, good question. What's an example of an ADT? Queues. A queue, we can make a queue using either a dynamic array, which is a data structure, or a linked list, which is a data structure, right? Stack would be the same. The only two data structures we've really used, well, I guess you could have 2.5. Trees you could kind of count too. But trees are a little weird because, well, trees I would say is a data structure, yeah. Right, yeah.
Sort of like the degenerate case, but just like a line. So like sort of how you use arrays, but like just in that sort of idea of having like a ordered set of things.
Yeah. That's the, what, data structure or the?
The abstract data type. So the data structure
Oh, yeah.
would be
Well,
an array, a dynamic array, a linked list.
Remember, we called it a list, right? Remember for homework 1, we had list dynamic array. And for homework 2, we had list linked list. Both lists, abstract data type, using two different data structures. Make sense? That's how we do that. OK? All right. Explain when a destructor is necessary in a C++ program. Anyone want to do that? Yeah, Alex.
Anytime you're using the new command or allocating memory?
Pretty much, yeah. If you're going to use new, you probably are going to need a destructor at some point. Not all the time, but most of the time, yes. Yeah.
Specifically, when one of the members of the class is declared with new.
When one of the members of the class is declared with new, that's a very good point. Yep.
Just by having this thing exist,
Mhm.
there will be some dynamic memory allocation.
Yes, and keep in mind it's after, like, it exists for the whole rest of the class,
Right.
and then you need to clean up. Yeah.
If you allocate memory for like an integer, you still have to delete that?
You do. Yeah, you do. If you allocate, which you can do, you can allocate memory for a single integer, but you would have to delete it. Yeah. Yeah.
Is default destructor in this case referring to something that's just like NA destructor and then just like has nothing in it?
Henye, tilde. Henye, I love that though. I haven't heard that one. Yes, that's just where it's empty, an empty function with a default destructor. In other words, if you're only doing these in your program, you could write a whole C++ program where you do just this. You never need to use delete, and you never need to have anything more than just the default destructor. Yeah.
So let's say you passed a pointer by reference to a function. So you had the address of a pointer.
Okay.
And within that function, you called new on that pointer to allocate memory
Yeah.
to that pointer. And then the function ends without calling delete.
Yeah.
Then does your pointer point to the memory you allocated?
Yes.
All kosher?
Well, what was it pointing to before? I mean, that's the problem, is you might have to worry about what it's pointing to before. So you have to be really careful, but that would work,
Nothing
sure.
got deleted, right? At the end of the function.
Yeah, nothing got deleted. No. No, in that case, nothing got deleted. Yeah, good question. OK, lots good. We do have a bunch of more things to go. Go.
If you allocate memory and then delete it outside of a destructor so that you have accounted for everything, do you still need to create a destructor?
No. But the problem is you're generally not going to know. Like you're generally not, but you don't have to. It's only if at the end of your class you've still got stuff you have to clean up. That's when you use the destructor to clean it up. Yeah.
Is there any reason that you have to write an empty destructor if you don't need a destructor, or can you just leave it out? Because
I think the compiler will do it for you.
Yeah, in Comp 11,
Yeah.
early classes, we just didn't write.
Yeah, the compiler will do it for you in general. But I like to do it explicitly so I know, hey, do I need to write it or not? And then, that's it. Jordan.
You only call a destructor on an array when you use the word new.
Yes. Yep. The only one you need to. Miranda.
Oh, never mind.
OK. All right. We already talked about these guys a little bit. Static and dynamic arrays. And this is actually Jordan's exact question, right? Differences between static and dynamic arrays. The big difference between a static and dynamic array is the flexibility with a dynamic array. Static array is like int a bracket 10. You've got 10 things to use for the whole program, right? That's not so good, because what if you wanted to use 11, right? If it goes up to 11, you're in trouble. Okay? So dynamic array is where you're going to use new, and you're going to be able to expand it, and you're going to be able to use it in much more efficient ways. Okay? Arrays are constant time lookup for the indexes. Why are arrays good? Because they're constant, because you can do random access, etc. Downsides to using arrays. Yeah?
They can be a pain. They can be a pain to sort and shift around.
They can be a pain to sort and shift around. Yeah, sorting arrays is not, it's not trivial. We'll learn sorting things later. Alex?
What is it? There's if you want to change something near the end of the array, you have to go through the entire thing.
Yeah, not always.
Like assuming that you don't know the exact thing.
Yeah, assuming it's not sorted, you would probably have to walk through the whole thing. Yes, good question. Yeah.
Short of using dynamic arrays, it's kind of hard to change size.
Right, yeah, if you don't use dynamic arrays, you can't change size. Yeah, good question. Let's see, we know how to expand dynamic arrays. We've done that a lot. Asymptotic behavior for dynamic arrays. Sorting through a dynamic, or searching through a dynamic array that's not sorted. And searching through one smartly that is sorted. Log n. Yeah, good. Removing from the front of a dynamic array? No. Linear if you're not going to delete the whole thing, yeah, or if you're not going to leave it. Linear, yeah. OK, good. Write an append function. I'm not going to make you do that now, but write an append function for a dynamic array. That's actually a pretty easy one, right? First check if it's at the end, so you need to expand, and then just tag on the last value right at the end. No moving. Charlie?
For those
I would tell you, I would say the expand function is written for you, or you'll call the expand function or something like that. Yeah, you don't need to write that explicitly. OK. Linked lists. Our first node-based structure, class or a struct. You got to walk through linked lists. No way to do that otherwise. Linked lists have heads, tails, sometimes, not always. So sometimes I could ask you about a picture, like to say, hey, draw on this picture what's going to happen to the nodes. Some people like that better. I'm not sure I'm going to do it this time. We'll see. Deleting a node in a singularly linked list. Remember what happens if you want to delete node whatever, you can't just delete node whatever. Why? Yeah, because you need the one before it, so you have to write the code to keep the previous. So go back over that code a little bit. Keep the previous node so you know how that works. OK. Let's see. Doubly linked lists forward and backward pointers. You can delete a node without worrying about the previous. Linked list operations. So you guys found out from homework 2 that there can be a little tricky, right? All those people who filled gigabytes of data with the loop that just went on and on and on. You found that was tricky. Circular linked list. We could talk about that a little bit. Nothing too special about that. Tail points back to the head. OK. Sample question. Find some errors in the insert before. So you could say, hey, you did forget to check this or move this pointer or whatever. Right?
In a find the bug type problem, would
Yeah.
you be expected to write the replacement code?
Yeah, I would tell you fix it. I would say something's wrong here. And sometimes fixes just delete it. Like that shouldn't be there. Cross it out. But otherwise, yeah, you'd have to fix it. And it wouldn't be something we'd have to rewrite the whole function, obviously. Something more easier than that. OK, recursion. Talked about this a number of times. Recursion is not magic, right? It does take a little bit of time to understand. It can be very beautiful. It can also be a little bit tricky because you don't think through the problem enough. And I find recursion really hard, so I'm with you. If you think recursion is tricky, well, you're not alone. Okay? Some people eat it up and they love it. I happen to have a little trouble processing it sometimes, so it's a little tricky. I will expect you to do. Well, you got to know about what is the whole deal with recursion. It's like a stack, right? When you call a function, the stuff gets saved on the stack. I'm not going to make you do too much talk about that, but you should at least understand it. You have to write a simple recursion function. We talked about that. Examples, Fibonacci sequence. Why did we say the Fibonacci sequence was bad?
So you end up doing the same operation.
Yeah, you do the same operation a number of times, and it's also exponential behavior. Terrible, right? OK, sample question. Write a recursive function to calculate the sum of the first n even numbers. Could do that. Right? That's, I think, a moderately tricky one. Not impossible, but moderately tricky. Remember, don't forget your base case. Don't forget to, in this case, you have to either add by 2, not hard, or if you're adding by 1, remember to skip the ones that are the odd numbers. Right? You should know how recursive functions and stacks are similar. We'll talk about that. Okay. All right, stacks. Why do we have stacks? Because they're easy, right? They're really simple. And what's the asymptotic behavior for push, pop, and top? Constant. That's why they're awesome, right? If you can find a problem that has last in, first out behavior, use a stack. It's awesome. Okay. Postfix notation, converting infix. I'm not going to make you do infix to postfix. We didn't really talk about that. Tree traversal is how you'll do that for the lab this week. Hopefully you guys have seen the pre-lab. It's actually, if you do the pre-lab, you will have no trouble on the lab. It'll be a pretty straightforward lab tonight and tomorrow. Yeah?
I don't know if you covered this yet, but if we learn to reverse an array, the order, can we just use a stack
To reverse an array, do you even need a queue?
I mean, no, but wouldn't that be a lot quicker? As in, if I just if I pop everything off and put in a queue and then EQ it and put it back in,
Wait. I think I can I think people can think of an easier way to reverse a string, let's say. How do you reverse a string using a stack? What do you think? What's that? You don't need a queue. We had Nathan?
You can just push them all on and then and then insert them as you pop them off.
Yeah, you just push them all on a stack, and then when you pop them all back off, they come in reverse order already. And so you just insert them into the end, or the end of the array. Yeah, not bad. Okay. Sample question for stacks. Explain the stack functions, top, pop, push. Explain the stack, how you'd use a stack to perform post-order traversal. You're going to do that on the lab today. Well, actually, you don't even do post-order on the lab. You can. It's like a kind of an extra if you get done with the other ones. How to use a stack to perform post-order. You'll do that on the lab today too. Well, same idea, you could. And then asymptotic notation we already talked about. Okay. All right, cues. First in, first out behavior. Right? You guys are getting sick of cues because of this homework assignment, but you guys will know them pretty well at that point. We normally call the functions InQ, DQ, and front. Today's lab, it will be push, pop, and front. Why? That's the way the standard template library does it, so do that. Why don't you need to move elements in a queue? Remember when we DQ, we don't do any moving, we just leave it right there? Why? Yeah, why? Yeah. Yeah, we move the front index instead of the array. And if we do circular, who cares about moving the array elements? It takes too much time. We want front to be order 1, O1. Yeah, Miranda?
If you cared about, like, it was, I don't know, you're putting sensitive data in your queue and you don't want it just sitting around,
Sure.
would you change it to a null or whatever value before you did it or at the end?
What do you mean before?
Like, as you were moving it, would you change it, or like once the function came out with like the final?
Oh, I see. I would do it right when if I was worried about it, I'd do it right when right when I saved it to be returned. Yeah. It would actually be even a little more tricky than that. But yes, that's what I would do it right then. Okay. Write the InQ function. I might ask you to do that. Right? Not hard. Okay. Then finally we got to trees. Well, not quite finally. Got asymptotic notation too. Trees. So trees were our next node-based data structure. Okay, you should know the vocab, root, depth, height. That's something you put on the cheat sheet, by the way. Right? I mean, if I ask you, what's the definition of the height of a tree? You're going to look on your cheat sheet. I mean, that's the answer, right? You're not going to memorize that. Children, parents, siblings, leaves, path lengths. I'm not going to ask about grandparents or cousins once removed, all that business. We could, so for a regular non-binary tree, we could link to all the children, but it'd be hard to do. Like it'd be you'd have to add another data structure. You couldn't do it just with like node pointers directly. What we can do is we could have this 2 links, first child and next sibling. You might want to look at that example that I did. That was a hard example, but you might want to look at that one and just kind of get a feel for how it's written. And then trees are like really, especially binary trees, inherently good for recursion because you can just recurse through the whole tree. Okay? Not as easily as linked lists, but you can. Okay? Let's see. Then we had binary trees, right? These are the ones with only a left and a right. If you don't balance them correctly, which we'll actually talk about next week, they degrades into linked list behavior. And we did look at binary trees using for postfix and then using a stack. And trees, all these orders you're going to test today and tomorrow in the lab. Okay? Yes?
So if you
Question?
combine like stacks and trees, you're doing like depth, would that be like stack?
Yes. If you're doing a breadth first search, it would be like you would probably have to use a queue. If you're doing a depth first search, you would use a stack, yes. Yep. Yeah, good question. And that's in particular, that's if it's not a sorted, like a binary search tree, because then we know that that's easier to do. Okay, binary search trees, the next topic here. Binary search trees are the ones where there's this invariant. And the invariant says, All nodes to your left are smaller. All nodes to your right are larger. End of story. Okay. The average depth for a binary search tree is log n. That's why you get logarithmic behavior out of it. Okay. You should know all the BST methods. Those are the easy ones. And then the one we spent a little time on, remove. You should know how to do the remove one. Okay. I didn't actually talk about lazy deletion. If you don't want to go through the process of removing, even though it's not that hard, you can actually leave a node there and just mark it as being gone. And so when you traverse to it, you go, oh, it's not here. It's actually deleted. So you could have an extra little thing. It's called lazy deletion, and it just saves you a little bit of time. If you're doing inserts and deletes, and you know you're going to do lots of inserts and deletes of the same node, why not? Make a lazy deletion where you say, oh, I deleted it now, but later it's going to be back, so I don't have to reinsert it either. I just go and mark it as there again. So that's called lazy deletion. You had a question, Brian?
Did the example codes from the last, it was last class when you said you were going to give like the answer codes, did those ever get put up? The mirror? Yeah, like a mirror.
No, I didn't put those up. Email me and I'll put them up today. Thanks. Yeah, good question. OK, here's an example of binary search. Describe how to insert or delete from a binary search tree. Which is harder? Well, we know delete's harder. OK. All right, and then finally, asymptotic notation. We've been doing this almost the entire class, right? This is how we compare algorithms. It's something big that if you're going to have two algorithms and you want to compare them, use the asymptotic behavior. Try to figure it out. OK? We could have done this by the primitive operations. Like that's the way we kind of started doing it. A lot of times we don't even worry too much about that. We kind of look at the overall structure and go, oh, I see what's going on. You pick out the important parts. Constants don't matter, right? And only the biggest function matters. Only the one that's the longest time. I'll show you an example. No, I won't. If we had something like this, n to the fourth plus n squared plus log n plus 250,000 n. What's the asymptotic behavior for this? Just n to the fourth. Right? What if I put a 6 n to the fourth? What would it be? Still n to the fourth. Right? Pretty simple. OK. These are the ones I care about. Right? Constant, logarithmic, linear, quadratic, polynomial, exponential. And then there's also n log n. I'm not going to ask you a specific question about this, but just know that this one also exists, and it's for searching. No, sorry, it's for sorting. I always get those two mixed up. It's always for sorting. OK? Order n log n. OK? Here's some hints on those. Constant behavior, not dependent on the number of elements. Order n means you access all the elements, or at least you have the potential of accessing them all. N squared, doubly nested loops. Log n, half, 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 half. Okay. All right, and sample questions. Oh, here we go. There's another one. What's the asymptotic behavior of this? N squared. Let's see. Analyze all the algorithms, determine the asymptotic behavior for the function. Yeah. Think that's it. Questions? All right, good luck on Wednesday. We'll see you in lab.